Number one says, which of the following is an example of a quantitative observation? Whenever you see the word quantitative, think numbers. Okay. So a piece of metal is longer than, that's qualitative. Solution one is darker than, the liquid in beaker A is blue. Those are all qualitative observations. The temperature of the liquid is 60 degrees Celsius. That's definitely quantitative. All right, so we have that D. Which of the following figures represents results that have high precision? Okay. Remember the difference between accuracy and precision. Accuracy assumes that you either know the true value or you know an accepted value. And if your measurements are close to the accepted value, then you will say that measurement is precise. If it's not close to the accepted value, then it's not precise. And in this case, our example is that of a bullseye. And the bullseye, of course, is going to be the true value or the accepted value. So which ones of these close to the accepted value? Well, if you take the second one, Roman numeral 2, none of those shots are anywhere near the center. Right? So it can't be that one. 3 is a good choice. 1 is, wait a minute, high precision. And nobody stopped me. I was thinking accuracy. High precision is grouping. So if we have close grouping, then you have precision. You don't have to have accuracy with precision, but it helps in the real world. So 2 and 3 are both show evidence of precision. That would be E would be that answer. Let's see. Would number 1 be considered accurate? You would have to average those values. Now, if we only had the outer ones, possibly, but the inner one skews it quite a bit. So I wouldn't even think 1 would be accurate. And when you're talking about accuracy, you don't have to, and you have more than one measurement, then you take the average of the values to find out if your measurements are accurate. You can have accuracy without precision. Okay, number 3. The amount of uncertainty in a measured quantity is determined by what? Think of operating a piece of equipment that's designed to make a certain type of measurement. All right. Is the equipment autonomous? Right. Will it do this without any human intervention? I don't know of any equipment that'll do that. Even just to set it up requires human intervention. So you've got the operator and how good the operator is at setting up the equipment or using it. And then you have the inherent accuracy and precision built into the instrument. So you have those 2 factors that are always required to assess the uncertainty that's associated with any measurement. And that would be A, both the skill of the observer and limitations of the instrument. If you want an instrument that's extremely accurate, then you need to have deep pockets, because the cost of incremental increases in accuracy, the cost goes like that. So we say, if you don't have deep pockets, then you learn the term good enough. So A is the best answer for that. The boiling of water is, okay, now we're talking about physical versus chemical changes. Boiling of water, think of the difference between physical and chemical change is identity. Does the identity of the substance change during the change? If it doesn't, then it's a physical change, right? And water, when it boils, it's still water. It's water vapor, steam versus liquid water. So the boiling of water would be a physical change only. That means it's either A or B. And then we look at the details. Because the water merely disappears. The water doesn't disappear, right? That defies the law of conservation of mass. The water changes and its chemical identity stays the same. That's B. Okay, number 5. A solution is also called this is introduces the idea of heterogeneous versus homogeneous mixtures. And homogeneous mixtures are uniform throughout. In other words, you can have different identities for the substances in the mixture, but if they're uniformly distributed, so any place you sample, you get the same composition of your substances, then that's homogeneous mixture. And that's also synonymous with solution. Which means that you don't have to have a solid dissolved in a liquid or a liquid in a liquid. You can have a solid dissolved in a solid. You can have gas dissolved in a liquid, a gas dissolved in a solid. You can still have homogeneous mixtures, solutions of any of those phases. So that's A. Which of the following has a different value on the moon compared to the Earth? Well, let's see what our choices are. Mass. Does mass change throughout the universe? Not in a Newtonian universe, right? If you get close to a black hole, then, or close to the speed of light, then you have changes in concepts. But in general, mass does not change. Time also doesn't change in a Newtonian universe. Time does change when you get close to the speed of light or close to a black hole. Right? But for our purposes, time is constant. Weight. The difference between mass and weight is mass is a measure of substance, how much is actually there, whereas weight is a force, and it's related to mass because more mass on the surface of the Earth will weigh more. But if you take the same mass on Earth and same mass on the moon, there will be a different force exerted by that mass on the surface of that body due to the mass of the body itself. Earth is the moon has 1/6 the gravity of Earth, so you'll weigh 1/6 as much as you do on Earth when you're on the moon. So that is the one that has a value different on the moon than on the Earth, is the weight. All the following are true except, okay, so we got to read through these. Ions are formed by adding electrons to a neutral atom. Is that true? Yeah. That's one possibility, right? A is true. Okay, so A is true. Ions are formed by changing the number of protons in an atom's nucleus. Yep. That's known as transmutation of elements. You change the number of protons, you get a different element. So B is can't be. Ions are formed by removing electrons from a neutral atom. That's also true. So that means we got to look for one that has both of the above. An ion has a positive or negative charge. Well, yes, that's true also. I was getting ahead of myself. So we got 3 that are true. An ion has a positive or negative charge. That's right. Metals tend, Oh, all are true except we're looking for the one false one. So metals tend to form positive ions. That's true. All right, so our answer is B because it's the one that's wrong out of all of those. It pays to read my own questions. Okay. Moving on. Number 8. All the following are characteristic of metals, except. Okay, metals are good conductors of heat. Oh, yeah. Are they malleable? Yeah, generally speaking, metals are malleable. Are they ductile? What do we mean by malleable versus ductile? Malleable is like they can be bent, or you can crease them with your fingernail or with a sharp object. Ductile means they can be stretched into thin wires. They're two different processes that are based upon the same atomic level activity. The ability of those metal atoms to slide past one another but still hold on is a concept that allows both malleable and ductile. You generally don't have one without the other. They're often lustrous if they're polished. If you've ever seen even a video of the precipitation of silver out of a combination of various substances, the way that they make Christmas ornaments shiny, they have this reaction, and I won't go into the details, but it deposits silver on the inside of that globe. And at first, when it first starts out, it's black. Right? Very finely divided metals are black. But as they build up their layer and they get more than just a few atoms thick, then they start to be lustrous and they'll reflect. So metals are often, that's why we say often lustrous. They don't necessarily have to be lustrous, depends on the conditions. Tend to gain electrons in chemical reactions. No, they give up electrons. Metals give up electrons, non-metals accept electrons. Generally speaking, unless you get close to that metalloid line, then they could go either way. But generally speaking, metals tend to give up electrons, not gain. So E is the outlier on this one. Which of the following is paired incorrectly? Okay. How about A? Strong acid is, what is that? H2SO4. If it's in aqueous solution. Sulfuric acid. Sulfuric. Sulfate becomes ick. Sulfuric acid. HNO3. Weak acid. Nitric acid is a strong acid. And this is in chemical terms. Strong versus weak. Strong in chemical terms means that those hydrogen ions are readily to leave the molecule. Right? Whether it's corrosive or not is another issue. That depends upon concentration. But strength in chemical terms is at the molecular level. So H2SO4, HNO3 give up hydrogen ions readily. So B is a false statement. Barium hydroxide is a strong base. Hydrochloric acid is strong. Ammonia is a weak base. So what do we mean by a weak base? A strong base versus a weak base is a similar concept to strong versus weak acid, but it's sort of the flip side of the coin. A strong base readily accepts protons, whereas a weak base does not readily accept protons. And if you, let's see, we're not going to do that experiment until the second semester, I think. Yeah. So I won't get into that detail right now. Okay, so the answer for 9 is B. How about 10? Which of the following are incorrectly paired? All right. These look like, except for the last one, symbols associated with the names. Is that lambda wavelength? Yep. How about frequency? That's not really a V. That's a Greek nu. And for that reason, you'll often see it rather than the nu, you'll see small f for frequency. So you may see it either way. But that one's true. Speed of light is designated as a small c. And hertz. Hertz is frequency. It's a unit of measure for that frequency. And it's actually how many cycles or how many crests do you see passing this point in 1 second? So it's like cycles per second. But cycles is not a dimensional value, right? So really, the unit of measure here is reciprocal seconds. That's a hertz. And X-rays, shortest wavelength. What's the shortest wavelength? Highest frequency, shortest wavelength. Gamma rays, right? X-rays are definitely short. I mean, they are, this is considered an ionizing radiation. But gamma rays have even shorter wavelengths and carry much more energy per photon. So E is the correct answer for 10. All right. About 11. I need to wet my whistle. Consider the following portion of the energy level diagram for hydrogen. For which of the following transitions does the light emitted have the longest wavelength? Okay. If we're talking about a hydrogen atom with 1 proton in the middle, and we have these different energy levels, 1, 2, 3, and 4, and the values are given there, we really don't need those values. We just have to recognize that further from the nucleus is higher energy. And if we're looking for the light emitted at the longest wavelength, long wavelength means low energy. So the lowest energy is the shortest jump for an electron. And that would be, and notice that the gap between the energy levels decreases as you move out. So the 1 to 2 is a certain distance, 2 to 3 is a shorter distance, 3 to 4 is even shorter. So if an electron jumps from 4 to 3, then that's going to be the lowest energy. Okay. And we do have that choice. A is from 4 to 3. That will give up energy. Now, if we went from 3 to 4, it would absorb that same amount of energy. So the key there is not just the distant jump, but whether it says light emitted or light absorbed. In which case, it would be the same value, except actually it would be inverted. Right? If it's absorbed, it would go from 3 to 4. Just in case I get sneaky and change the wording. Okay, so that was A, wasn't it? How about 12? Which of the following statements best describes the Heisenberg uncertainty principle? What Heisenberg said was essentially for objects as small as subatomic particles or even atoms, There are two defining estimates about these particles. One is the momentum, right? That's the Greek letter rho, which is mass times velocity. And the other is position, which we just give it an x, right? So the difference, the uncertainty of these values is given as a delta, right? The difference between where it is and where we think it is. If this is large in position, then that delta will be big. Okay? Momentum, since the particle is not going to change its mass, we're talking about velocity. How fast is it going, or how much energy does it have? Right? And if that's a delta, then it's primarily due to its speed, its velocity. And by interpretation, it's energy. So if this value is large, then the energy that we think it has and the energy that it has, there's a huge discrepancy. It could be there, but it might just as well be over here in terms of energy, right? So this delta means an uncertainty of. So what Heisenberg said was, if we know one of these with a high degree of certainty, where this delta is very small, then the other one's going to be huge, very large. We can't know both of them with any degree of certainty at the same time. That's why we generally use probabilities here, where we say, especially for electrons, the electron is going to be in this region somewhere. It's more important that we know what is its likely energy. That's more useful than position. So which one of these statements gives you that? C says it's impossible to accurately know both the exact location and the momentum of a particle. That's Heisenberg's uncertainty principle in words. <clears throat> 13. Okay. Which of the following is an incorrect designation of atomic orbital? All right, remember the four numbers that we have available for the quantum definition. The quantum definition of an electron is principal quantum number, then the magnetic quantum number, and then no, this is the angular momentum quantum number, the magnetic quantum number, and then the spin quantum number. Right. This one can be anything from 1, 2, 3 on up to however many. This one would take any one of these, and it would go 0, 1, 2, up to n-1. And then take any one of these, it would be minus L to 0 to plus L by whole number increments. And this one is only plus 1/2 or minus 1/2. So if we said 1s, and by the way, these would be S, P, D, and if this was 3, it'd be F. Right, letter designations. So if we have 1, can we have an S? Yeah. Right, so A is good. How about B? 3D. Well, if we have 3, then we could have 0, 1, or 2. We could have a D. Yeah, that works. How about 1P? If we have one, we can only have S. We can't have a P. So C is bad. If we went to 4, then 4 could be 0, 1, 2, or 3. So that one would be equally as valid. And then 6, any of these will have S's. I mean, each one, all of them will have S's. Only the 2s will have P's. Only the 3s will have D's. Only the 4s will have F's. So any one of them, up to 6, yeah, S will be there. Okay, number 14. Which of the following was not an elemental property usually predicted by Mendeleev for as yet unknown elements? Well, Mendeleev knew about atomic masses. They also knew other physical characteristics like density and boiling point, and definitely oxide formula, because most of the elements in the Earth's crust are combinations of oxides. Right? There are other possibilities like sulfides and fluorides and whatever, but oxide was a common way of isolating elements. You could isolate an element from an ore by extracting its oxide. So the oxide formula was well known. But electronic configuration, they had no idea about that at the time that Mendeleev was active. That came later. Not too much later, but later. So A was one that he knew nothing about. All right, 15. Which of the following atoms has three electrons in p orbitals in its valence shell? All right. So let's see. We have A, B, C, and then D, and none of these. So we'll just look at these. Barium, gallium, vanadium, and bismuth. Okay, you need your periodic table for this one. Rather than try to draw out the electronic configuration, just use your periodic table. Where's barium located? Barium is in the second column. It has 6s. 2 is its highest orbital, its valence shell. So what's the question again? Which of the following atoms has 3 electrons in its p orbitals? By the time barium gets to that point, by the time the elements get to the barium point, all the p orbitals are full, right? So it has how many in the p? 6. 6 electrons. So barium's full, right? P orbitals are full for barium. How about gallium? Well, gallium has 1, 2, 3 p's are full. Now it's getting into 4 p's, right? It's in the fourth period, and it's on the right hand side where the p orbitals are being filled, but it's only got a 4p1. It doesn't have 3 and only has 1 electron. So that's not it. How about vanadium? Well, vanadium is a transition element. We're filling 3 Ds there, right? It has a 3D3 there. But all its P's are full, right? It has full P's. Bismuth where's bismuth? Here it is. Bismuth's in the 6th period. And how many? Tellurium, lead, bismuth. 3 over in the P section. It has 6P3. There's your answer. Okay. That's an effective use of the periodic table to answer this question. 16. The force between two bodies having identical electric charge. Anytime you have the same charge, those particles are going to repel one another. So it is a force of repulsion. That's A is correct. It's not a force of repulsion if the charges are negative and one attraction positive. They're only attractive if the charges are opposite. Right? So B can't be it. Increases as the bodies move further apart. Now, the force of repulsion or attraction increases as they get closer together. D says independent of the distance between them. Nope. Now, Coulomb's law says as they get closer, they're more attracted. Directly proportional to the distance. Actually, it's indirectly proportional to the square of the distance. So as they get closer, it's inversely proportional. To make the distance smaller, the force gets bigger. But not only that, as you get closer, the force gets bigger by the square of that distance. So E's not right either. A is the only proper answer to this one. (17) Which of the following has 61 neutrons, 47 protons, 61 neutrons, 47 protons, oops, not neutral proton, and 46 electrons? Okay, what are we going to do first? We're going to find out which one of the elements is correct by the number of protons. 47 protons, we go to our periodic table. 47 protons is silver. So there's the correct symbol. That means either B or E would be correct. So we would have 47 here. And that means that the mass number would be 108. But we're missing an electron, which means it's unbalanced toward the positive by 1. It has a 1+ charge. Okay, that gives us B. All right, 18. All the following are in aqueous solution. Which is incorrectly named? A, B, C, D, and E. All right, H2SO4 in aqueous solution. It has an oxygen, so we don't say hydro. So we look at this part, the polyatomic part. Sulfate, H become X. So we just say sulfuric acid. Okay, that one's correct. H2CO3. Similarly, we look at this part. CO3 is carbonate. H becomes ic. So it's carbonic acid. That one correct? Yep, that one's correct also. C, H3PO4. Okay, again, we look at this part. Phosphate becomes phosphoric acid. And that one's correct. HCN has no oxygen. So we start with hydro. Then we look at this part, cyanide, ide becomes ic. So this is hydrocyanic acid. And that one's wrong. Okay. So there's probably our answer. And the last one is HCl. Chloride becomes ic hydrochloric acid. So there's your answer. D is the one that's incorrectly named. 19. A manometer. What's a manometer? Let's see, meter means to measure. It's a man measure. Oh, it's a device used to measure the pressure of an entrained gas of some kind. So it's attached to the vessel on the left, which is 2.34 liters in volume. Right. 2.34 liters. It's attached to our manometer. And the mercury level in the arm of the manometer attached to the gas sample is 24.3 torr lower than that of the arm open to the atmosphere. So this manometer is like this. And this end is open to the atmosphere. Okay. And the mercury in this one is 24.3 torr lower on this side. So this level down here is 24.3 torr difference. Okay. What else do we need to know? Atmospheric pressure is 1.23 atmospheres. Okay. So that's pushing down here, and the gas here is applying its own pressure there. So which side has the higher pressure? This side. Right. It's not only balancing the atmospheric pressure, but it's also raising 24.3 millimeters of mercury above this level. So the pressure inside the vessel is higher than outside the vessel. Okay, what is the pressure of the sample of gas? Well, it has to balance that pressure, atmospheres, plus this pressure. Can we add those together to find out the pressure? No. Apples and oranges. So we look at our choices, and they're all in torr. So we need to convert this one to torr. Right? How do you convert atmospheres to torr? What's a torr? It's a millimeter of mercury, right? So 1.23 atmospheres, we want to convert to torr. So atmospheres on the bottom to cancel and torr on the top. So 1 atmosphere is 760 torr. So 760 times 1.23 will then be added to 24.3. And if we do our math right, we should get 959 torr. Okay. It helps to draw a picture sometimes. All right, number 20. Consider a gas in a 1 liter bulb at standard temperature and pressure. It's connected by a valve to another bulb that's initially evacuated. Answer the following concerned about. What occurs when the valve between the two bulbs is open? So we got 1 liter bulb on this side connected to another, and we don't know what size this one is, but it's a vacuum. And this is 1 liter. At standard temperature and pressure. So this is going to be, we're talking about gases here. So this is 0 degrees C, and pressure is 1 atmosphere. Okay. So what's going to happen when we open that bulb? Well, we know intuitively the gas is going to go whoosh until we get a balance in pressure. Okay. But the question is, what's true about the value of delta H? Well, if this whole system is at standard temperature and pressure, delta H doesn't change. Delta H is equal to 0. Right? That's just a fact. By design. The experiment was designed that way. How about while we're at it? Well, Q is also going to be 0. This is the potential. This is the actual. Right? And work. Was there any work done? No. How about any change of internal energy, which is Q plus W? That would have to be 0 then, wouldn't it? Okay. All right. 21. In which group do all the elements have the same number of valence electrons? How do we know valence electrons? What's the easiest way to find the number of valence electrons for any set of elements? Periodic table. Yeah, just go to the periodic table. If they have the same number of valence electrons, they're going to be in the same group. So let's see. Phosphorus, sulfur, and chlorine. Well, phosphorus, they're in the same period, not the same group. Right. So A is bad. How about B? Silver, cadmium, argon. Well, we know argon's a gas and silver and cadmium are metals. So we know that's not going to be true. And if you can prove it by the periodic table, that won't work. Sodium, calcium, barium. Well, sodium's in the first column, so it has 1 valence electron. Calcium and barium are in the second column. They have 2 valence electrons. So that doesn't work either. How about phosphorus, arsenic, and selenium? Phosphorus and arsenic are in the same group, so they have the same number of valence electrons, but selenium's in the next group over. Right? It doesn't work either. So none of the above. Right? None of those have the same valence electrons. All right, 22. The ground state electron configuration of selenium is, and this is an abbreviated form. So we can start with argon, which has 18 protons. How about, was it selenium? Yeah, selenium. How many does selenium have? 34. Right? So what do we have? We have 24 electrons left over. We got to put in there. Well, if we start with argon, then we'd have to move to the next. We have to move to the 4th period. And we have 4s2 is the next. And then we come all the way across 3d10. Right? When you go from in the period, when you go 4th period through the transitions, you drop down 1. That's full. And then we go back up to 4p. 4p. So we've used up 12, we used up 30. 4p6 is all we can do. So 18 and 18 is 36. That's too much. We need 4. Now, is that right for selenium? Yeah, selenium, gallium, germanium, arsenic, selenium. That's 4. 4 over in the 4p. That's it. So 2, 10, and 4 would be A. Okay? And you can do that with any of the elements. I threw something different in there. Just keep building your atom, and you know what's being filled in what position. 23. Which of the following bonds would be the most polar without being considered ionic? Okay, so we better put all of them up here. Because when it says most, we got to compare. MgO, let's see, CO, OO, SiO, and NO. Okay, we got two conditions here. Most polar without being ionic. So we need polar and non-ionic. So the easy way to tell ionic is metal, non-metal. Right? Magnesium and oxygen would be ionic, so that's out. Now the rest of them, we can say this one's not polar. Right? We got rid of these non-ionic. Now we get rid of the non-polar. Then we just compare carbon, silicon, and nitrogen and their distance from oxygen. So nitrogen's right next door. Carbon is one step over, so it's a little more polar, right? Yeah, but silicon is over and down, so it would be the most polar. Now, depending on its environment, it's possible that this could be so polar that we might put it in the ionic stage. But for simplicity's sake, the silicon-oxygen bond we consider is the most polar without being ionic. And that's due to the fact that silicon is a metalloid. 24. Which of the following atoms cannot exceed the octet rule in a molecule? All right. And the hint there is consider the orbitals that are available. If we're going to exceed the octet rule, we have to have d orbitals available. Right? So that means n equals 3. Right? Then you could have L would be 0, 1, 0, 1, and 2. S, P, D. So now you have D available. So N has to equal 3. It's got to be in that in the third period or access to. None of the elements in the second period have access to d orbitals, but those in the third period do have access. So silicon, phosphorus, sulfur, chlorine, they have access to the p orbitals. So which of the following atoms cannot exceed the octet? Well, sulfur can, phosphorus can, iodine can, but nitrogen cannot. Nitrogen's in the second period. It does not have access to p orbitals. At least not in its ground state. So that would be A. Uh, 25. Which of the following has a zero dipole moment? All right. If you remember having drawn these in the past, that's great. If you don't remember, then you're going to have to go through the whole procedure. Draw the Lewis dot structure, determine the bonds are polar or non-polar. If they're polar, then you have to look at the geometry. Right? So if we look at ammonia, the geometry a triangular base, so it's tetrahedral, but the bonds are polar, plus you have that lone pair up there. This molecule is polar in that direction. NO2. I better draw this one. Let's see, this is 5 valence electrons, and 2 times 6 is 12. So that's 17 electrons. Minus 4, that's 13 left over. 2, 4, 6, 8, 10, 12, 13. This is one of those oddballs that the valence bond theory doesn't handle very well, because there's an unpaired electron in there. If we want to make an octet for this one, we can do 2, 4, 6, 7. We can't even make an octet. We either make an octet or we exceed the octet, one or the other. Right. But as far as the structure goes, it would be trigonal planar. That's 1, 2, 3 groups. And then it would be bent in order to give us, and oxygen is more electronegative than nitrogen, which will give us an overall dipole that direction, even though we have that one electron up there. So B is going to be polar. It's just not easily handled by the valence bond theory. And that's why we had to come up with something a little better. Molecular orbitals. Molecular orbitals will handle that a whole lot better. PF5. See, I can't even remember that one. Let's see, this is 5 and 35. 7 times 5 is 35. So that's 40 electrons. So we have P and then F. Let's see, 2, 4, 6, 8, 10. I've got 30 left over. 2, 4, 6. 6 times 5 is 30. We use them all up. So the bonds are polar toward the fluorine, but this is a trigonal bipyramid, and it's symmetrical. So this one's going to be nonpolar. It has polar bonds, but they all cancel each other out. So this would definitely be a zero net dipole. And we don't have any all of the above, none of the above, 2 of the above, that kind of garbage. So we found our answer. If we go to SO2, it's going to be bent and polar, and hydrogen cyanide is definitely polar. It might be linear, but this bond is polar, and that extra lone pair out there gives it a dipole moment this way. Okay, so we found our nonpolar one right there. All right, 26. The hybridization of the central atom of xenon pentafluoride cation. Here we go. So how many electrons do we have? Well, we have 8 there. 7 times 5 is 35, minus 1. Right. If we take away an electron, that gives us an extra positive charge. That's why I took an electron away. So that's so 42. Is that right? Yeah, 42 electrons. 5. That Okay, so that's 10. We have 32 electrons left. We're going to use up 30 of them, 5 times 6. And that leaves 2 more that have to go here. Okay, so hybridization. Around this central atom, we have 1, 2, 3, 4, 5, 6. 6 groups needs D2sp3. 3, 4, 5, 6. Okay. 27. All right. Which molecules have p orbitals that share an electron pair to create pi bonding? When you see represented here, the molecular formulas are given and the structures are given to show you where the double bonds are. Those are all pi bonds. So structure 1, 2, and 3, all 3 of them have pi bonds. So p electrons must be shared to make those pi bonds. So all of them have p orbitals that share an electron pair to create pi bonding. Right, so the answer is D. All of them have that. Now, the one on the left, which is, and remember the way we organic we write these molecules. Each one of these is a carbon. Right? And if we have benzene, that one, we also have an unwritten hydrogen around each one of these. Okay. This is a special case. Aromatic molecules, they don't just overlap p orbitals to make a pi bond. Aromatics overlap in a ring to make a conjugated system that is extremely stable. You don't see that in the second or the third one. But in the benzene, you do see that. And the aromatics are very stable. 28. A species has the following molecular orbital configuration. This substance is. Okay. Let's see. Do I need to write that? Yeah. It didn't allow us to reach the end of the line. Sigma 1s, 1s star, s star. The next one should be 2s and sigma 2s star, and then sigma 2p. This is there's no mixing in this one. Okay, then we have 2, 2, 2, 2, and 2, and 2. Okay. So for this particular molecular orbital system, is it paramagnetic or diamagnetic? Well, paired, 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 unpaired. It's paramagnetic. Okay. Then with how many unpaired electrons? 1 unpaired electron? Nope. That's 2 unpaired electrons. So B is your best answer. All right. 29. Which of the following contains the strongest bond? All right. I've already got it on the board, so I'm not going to write it up. If we draw the neutral dinitrogen molecule, we get a sigma 2s, sigma star 2s, pi 2p, sigma 2p. So there's mixing there. Remember, the pi is swapped with the sigma. And then we get pi star 2p. So in the neutral N2 molecule, we have 2, 6, 7, 8 minus 2 antibonding. Means 6 divided by 2 is 3. So we have a bond order of 3 for the neutral. If we add an electron, where is it going? It's going into an antibonding orbital. So that reduces by half. If we put another one in there, makes a 2 minus, that also goes in antibonding, reduces by 1. So we go from a 3 to a 2.5 to a 2. If we subtract an electron, we're subtracting it from a bonding orbital, which also reduces the bond order by a half. And if we subtract 2 to make a 2 plus ion, we're subtracting 2 from bonding orbital. So that decreases by 1. So the strongest bond of all of those is the neutral N2 molecule. All right. 30. Equal masses of hydrogen gas and oxygen gas are reacted to form water. Which substance is limiting? Okay. So first we have to say hydrogen gas and oxygen gas react. Form water. And it doesn't matter if it's a liquid or a gas in this case. But to balance it, we need 2 oxygens. Now we need 4 hydrogens. So that's balanced. Okay. Equal masses. So let's just say, I don't know, let's keep it simple. Say, what would be the 1 mole of O2? Would be 32 grams, wouldn't it? Yeah, 16 plus 16, 32 grams. So if we make this one 32 grams, that makes this one 1 mole of oxygen. But how many moles of hydrogen does that make? Well, hydrogen is about 2, right? So we can rough it out at 16 mole, right? Okay. So which one's limiting? Oxygen, because it's a 1 to 2 ratio. It only needs 2 moles of hydrogen to give us water. And by that time, all the oxygen's used up. So oxygen is limiting in this case. That's the simplest way to explain it. Since it said equal masses, I'll just pick the mass I want. Okay, how about 31? Okay, 45.9 gram sample of metal is heated to, oh, this is a calorimetry problem. All right, so we've got 45.9 grams of a metal. 45.9 grams. Yeah. And this is the mass of the metal. And the initial temperature of the metal is 95.2 degrees. 95.2 degrees C. And place it in a calorimeter containing 120 grams of water. So the mass of the water is 120.0 grams. And the initial temperature of the water is 21.6. Temperature initial of the water equals 21.6 degrees C. See, I pull everything out of the problem and put it on the board so I know where I'm at. The final temperature is 24.5. So the final temperature is 24.5 degrees C. All right. This is going to be the final temperature of the water and the metal because we put them together, right? So when we lay out our formula, then this is going to be the final temperature of both of them. Now, it doesn't include the calorimeter, so we have to assume that the calorimeter has no contribution. So everything that happens in Vegas stays in Vegas, and the heat for the metal plus the heat for the water added together equals 0. Okay. So how do we express the heat for the metal? Well, we have the specific heat for the metal times the mass of the metal times the change in temperature for the metal. Similarly for the water, and the mass of the water and the change in temperature. Okay. All right. So what's the specific heat for the metal? It's unknown. That's the question. So it stays as is. The mass of the metal is 45.9 degrees, 45.9 grams. Temperature change is final minus initial. So the final is 24.5 degrees. Minus the initial, 95.2 degrees C. Okay. Now, specific heat of water is given as 4.18. So this is a square bracket these. This is going to be 4.18 joules per gram degree C. The mass of the water is 120 grams, and the change in temperature is final minus initial. Final is the same as the metal, 24.5, minus the initial, which is 21.6. There we go. So now we have an equation in one unknown. We can solve for it. All right, so we can do this whole thing right here. 24.5 minus 21.6, and then times 120, and then times 4.18. So this one, this side, is going to be a positive 145.5. And grams cancel, degrees cancel, so this is joules. On this side, this is going to be our unknown, but we can resolve this part of the equation. So 24.5 minus 95.2 times 45.9. So this is times a minus 3,245. Okay. So now what do we do? Well, we got to get all our unknown terms on one side and our non-unknown terms on the other side. So this is going to be a negative value. If we bring it over here, it'll make it positive. So why don't we do that? 3,245 SM now is positive 1455. And SM, actually the units of measure here are grams degree C. Right? So this is grams degree C on this side, and this is joules on this side. So if we take this one, SM, let's see, I kind of got those mixed up. We solve, well, the specific heat of the metal then this 3245 plus the grams degrees C come over here on this side. 3245 grams degrees C and 1455 joules. So now we've reestablished our units of measure, joules per gram degree C, just like that one. We just need to divide. Let's see. Wait a minute. Let's change that side. There we go. And this comes out to 0.45 joules per gram degree C. 0.45 is iron. Okay. I thought I'd better work that one out completely. Because once you start getting into these calculations, you have to be very methodical about it, or you get lost, as you've seen me do on numerous occasions. All right. So let's see, what do we got next? E. How far along are we? Is it following along with the handout? Okay, that's good. We're probably close to the end, aren't we?
I think there was this
We got a few more, yeah. We got time.
40.
I'll take the pressure off Thursday if we can finish. 32. Nitric acid was first prepared. All right. Remember word problems. What are word problems designed to do? Confuse. And they throw in a bunch of extraneous information sometimes that you don't need. So you got to pick out what you need. The fact that nitric acid was prepared 1,200 years ago is beside the point. Now, the description of how they did it is summarized in the equation. And we want to calculate the delta H for this balanced reaction given the following enthalpies of formation. All right. So if we have this equation with sodium nitrate, sulfuric acid react together to make sodium bisulfate or sodium hydrogen sulfate and nitric acid. Of course, the nitric acid comes off, actually, it's hydrogen nitrate because it's not in water yet. But what they'll do is, well, you had two options nowadays you do. You could cool it, condense it into pure HNO3, but they probably bubbled it through water. And the more they got bubbled through water, the more concentrated it got. But that's beside the point. What we want to do is use these heats of formation to determine the delta H for this reaction. Remember, delta H is going to be, for the reaction, is going to be the sum of the heats of formation, delta H formation, of the products, minus the heats of formation for the reactants. And we have to include the number of moles of each. And we look through the coefficients for that. In this case, the coefficients are 1. So we don't have to worry about that. Right? We just use the raw values. So we say sodium bisulfate is minus 1125.5. Minus 1125.5. And they're all in kilojoules. And the next one is sulfuric acid, which is minus 814. Minus 814 kilojoules. And then we subtract the heats of formation for the, oops. Y'all didn't stop me. Good thing I caught myself. Products first. Nitric acid. 135.1. I would have figured it out eventually when I got the wrong answer. Okay, now we go to the reactants. Sodium nitrate, which is also known as saltpeter. Minus 467.8. Minus 467.8 kilojoules. And then, so the heats of formation of each one of these is negative. That means to make these things, you generate a lot of extra heat. Now, the overall reaction, we're not sure yet. What we have to do is add these together. 1125.5, change the sign. And then 135.1, subtract that one. This is minus 1260.6. And then minus whatever this one is. 467.8, change sign. And then 1125.5, subtract that. So this is minus 1593.3 kilojoules. And then this one changed to a positive sign. Right. And that gives us 332.7. That's positive. So this is an endothermic reaction, which is probably good. It gets cold. Now, how did I get the wrong answer?
How to figure out.
Let's see if I put the right numbers up here. Product. This one's wrong. Oh, it's H2SO4. Yep. That's the problem. 814. Okay. In that case, the answer should come out 21.2. And it's still endothermic. See how easy it is to get messed up. Okay. That's short answers. That reminds me. If you take the exam in face to face, of course, I'll grade it on the spot. But if for some reason you have to take it in Brightspace, these answers where you have to put in values, I have to grade those manually. So you won't get a grade back right away. You do it that way. Okay, so complete the following table. If we have 55 Mn3 plus, 33. I'm going to put the 25 here because you're going to have to look it up anyway. Number of protons is 25. Number of neutrons is 25 from 55 is 30. Number of electrons is, we're short by 3 electrons. So it'd be 22 electrons. Atomic number 25, mass number is 55, and the charge is 3 plus. Write the names of the following compounds. Okay. This type of question gave people fits at the beginning of the semester. FeSO4. Let's just do it like this. D, E. Okay, we've got these formula. C2H3. C2H3O2. AgCl. CaSO4. And N2O3. Okay. First question you ask yourself when you see a formula. Is it metal, non-metal, or is it non-metal, non-metal? This one is metal, non-metal. It's metal polyatomic ion. So it's either going to be type 1 or type 2. The tiebreaker is, can iron have more than one charge in a compound? And the answer is yes. It's a transition element. And it's not one of these three. These three are fixed. But the rest of them are variable. In fact, some of these are variable also. Okay, so that means we need iron, and we have to figure out what its charge is, and we have to say that's SO4, that's a polyatomic ion, so it needs a name, right? And you've got a chart with that name in there. It's not that chart. But when you look it up, it's sulfate. And sulfate has a 2- charge. So that means iron has to be a 2+ charge. There's your name. Okay. Metal, non-metal. Sodium, though, is a fixed charge. Right? It's an alkaline metal. It only has +1 charge. That's it. It's type 1 compound. So we only have to say sodium. Right? What are the naming? What are the driving force behind naming compounds? We want the name to be unambiguous. Right? This name is associated with that compound, none other, and non-redundant. We don't want to say something twice. So we don't put the charge for sodium in here. We don't need to. And then this polyatomic, you look it up, it's acetate, the -1 charge. Right? So we say sodium acetate. That's it. Okay. Metal, non-metal, but silver is one of those that has a fixed charge. Right? It's a copper silver cadmium. Yeah. So we don't have to say what the charge is. Silver chloride. And for this part of the molecule, we change the ending to IDE. It's not silver chlorine, it's silver chloride. Calcium is a fixed charge. It's a metal, but it's a fixed charge. So we only have to say calcium. Sulfate. This one is non-metal, non-metal. So when we name those compounds, we just have to say how many of each using Greek prefixes. This is dinitrogen. Trioxide. That's it. Right, 34. And 35, we go the other direction. Let's see, is there any down here? No, it's just these two. A and B. First one is aluminum hydroxide. The second one is sulfurous acid. Okay. Aluminum is one of those metals that is fixed charge. It's a 3+ charge. So with aluminum, 3+ charge, and hydroxide is a polyatomic ion, OH-. So to balance it, to balance the charge, we need 3 hydroxides. right? And all the polyatomic ions, if you're going to use more than one of them, you have to use parentheses. Sulfurous acid, right? So we know it's going to be like that, and maybe more than one. And then where does the sulfurous come from? Us comes from ite. Sulfite. Sulfite is SO3, 2 minus. So that means we need 2 of those. And this is aqueous. Now we don't have to write that in the name. H2SO3, aqueous. All right, let's see. 36. With the following data, use Hess's law to find the change in enthalpy at 25 degrees for the following equation. All right. So our target equation is calcium carbide plus water yields calcium hydroxide in aqueous solution plus acetylene gas. And if you were a retired coal miner, you know exactly what that means. That's your lamp. Put some crystals of calcium carbide in that little canister in the front, add some water, bang it up, strike it, and you get a light. It's not a very bright light, but it's a light. It's also hazardous. Open flames are hazardous in coal mines. Okay, anyway, we're going to go back and we're going to find out from this set of 5 equations, what is the enthalpy change for this reaction. So what you have to do is decide, all right, what do you have? What do you need? If we just start from this side, calcium carbide, which one of these has calcium carbide in it? The first one. But it's on the wrong side. So if we flip that equation, and there's only one calcium carbide in the component equation, then all we have to do is flip it. So we have calcium carbide for our first equation. Yields calcium solid, right? Yes, yeah, calcium solid plus 2 carbons graphite. And the delta H for this is the opposite sign, plus 62.8 kilojoules. Okay, so it takes care of this one and this one, but we've added a couple. So we know we're going to have to get rid of them eventually. How about water? Which one has water? I think we ought to skip water for now, because it's going to be in one of these equations. Let's go over here to calcium hydroxide. Calcium hydroxide on the right-hand side, and the third equation does have that. Calcium hydroxide on the right-hand side. And on the left-hand side, we have calcium oxide and water. Calcium oxide plus 1 water. Okay, so it takes care of this one. That one's done. Now we need acetylene. So which one has acetylene? The fourth equation has acetylene on the wrong side. So we're going to have to put that one on this side. Oh, I forgot the value here. We didn't flip this one. All right, so it's minus 653.1. Okay. So now we're going to put acetylene on this side, which means we flip that equation. And acetylene on this side also has in that equation 5 halves oxygen. Okay. On this side, we have CO2, 2 of them. 2 CO2s and 1 water. Okay. So it takes care of this one and that one. And the value now would be, change the sign, be plus 1,300 kilojoules. Okay. All right. We got those two right here. Now, what do we have that we need to get rid of? We got calcium oxide, we got calcium, we've got graphite, we've got oxygens, and we got carbon dioxides. So what do we have left? Well, we have the first equation, which has, no, we already used that one, sorry. First equation we used. We skipped the second one. Calcium oxide is on that side. It needs to be on this side. So if we take the second equation and flip it, we're going to have calcium. Oops, no, we don't. Why not? Because we want to cancel it. So we want it on that side. And that's where it is. Because we don't want it in this equation. We want to get rid of it. So calcium oxide solid on this side and 1/2 O2 on this side with calcium solid on this side. And that's minus 635.5. All right, were we successful? Calcium oxide, calcium oxide, calcium, calcium. Okay, half oxygen. We're going to save the oxygens because there may be another one come along. Well, let's see. We've got this. Oh, graphite. Who's got graphite? The bottom equation. Graphite is on this side of our equation. Graphite is on the left-hand side of that one. That's exactly where we want it. So we got graphite plus oxygen yields CO2. That's minus 393.51 joules. Okay. Oops. We need 2 of each, though, don't we? Yeah. We need 2 of those. We need 2 of these. Okay, so we have to multiply by 2. Oh, and this one's got to be multiplied by 2 also. So that's 2, 0, carry 1, and 6 is 7, 18, 7. Minus 787. And that makes this one 2, this one 2, and this one 2. Okay. So 2 graphites cancel 2 graphites. 2 carbon dioxides cancel 2 carbon dioxides. And now we have 2.5 oxygens over here. 5 halves is 2.5. Right. Okay. So we cancel all the oxygens also. Okay. And all we have left is that, these 2, and that one. Okay, we're good. Now we can add them all up. Find out what the value is. 62.8, 653.1 subtracted, 1,300 plus 635.5 subtracted, and 787.02 subtracted. And I get minus 7.8 kilojoules. Rounded off 713. Okay. That's a lot of work. 37. Let's see, what is lamp over? 350.
I think so.
Yeah, 350. Okay. We still got a chance. All right, 37. Which of the following has the largest first ionization energy, sodium or rubidium? Remember the periodic trends. Here's our periodic table. And we've got hydrogen up here and helium up here. And first ionization trend. First ionization values decrease, increase from left to right, right? And from bottom to top. So first ionization energies, increase that direction. Okay, so sodium and rubidium are in the same, rubidium's down here, sodium's up here. Actually, it's higher. Sodium's up here. So the higher first ionization energy is going to be sodium. How about largest atomic radius? Okay. Take this out of the picture. Atomic radius increases from top to bottom because you're adding electron shells, right? And from right to left, it increases. From left to right, it decreases the radius because of effective nuclear charge is increasing, which draws those electrons in. So increasing atomic radius decreases from lower left to upper right, or increases from upper right to lower left. Yeah. And if we're trying to find the largest atomic radius, and we're looking at nitrogen and oxygen, nitrogen would have a greater atomic radius than oxygen because it has fewer protons in its nucleus. It's on the left. So nitrogen would be the answer for 38. Let's see. This one is, what do we say? So sodium, and this one's nitrogen. 39. Consider the structure of glycine. Anybody know what glycine is? It's an amino acid. It's chained together with other amino acids to make proteins. Okay, glycine is this. Let's see. Yeah. Let me draw it the way they've got it. So this is the carboxylic acid side. And this is the ammonia side, or the amine side. And then the other two positions are that and that. Now this part right here is the amino acid. And it's always the same in every amino acid. This part right here changes. For glycine, that's a hydrogen. Right? For others like alanine, this would be a CH3 or a methyl group. So this is the part that changes among the different amino acids. That's neither here nor there. They've labeled this one as carbon 1 and carbon 2. Right, now the question is, what's the hybridization at each nitrogen and carbon atom? All right, so carbon 1 has three groups. So that's sp2, right? That's one. This is two. And you know that there are no lone pairs there because carbon prefers 4 bonds. Right? And it's got 1, 2, 3, 4. In fact, it's got its octet. This one has its octet. But its octet gives you 4 groups, which is sp3. The nitrogen might give you some trouble. The nitrogen sticking out here like this has a hydrogen and a hydrogen and a lone pair. Okay. So it's going to be sp3. That's the trick to this one, because the lone pair is not in there. You have to know it's there from previous examples. And it's like ammonia, right? Ammonia has that lone pair. And in this case, we make an amine out of it. That is, we only have 2 hydrogens, and the other bond is given over to a carbon. So that's the trick to this one. Oh, how many bonds are in the molecule? All right. Okay, so we got, and it doesn't specify, just any bond. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 bonds. Gotta be sure and count them all. How many pi bonds? There's only 1 pi bond in this whole molecule right there. All right. Number 40. You're holding 2 balloons, orange balloon and a blue balloon. Let's see, are they different sizes? The orange balloon is filled with neon and the blue is filled with argon. The orange balloon is twice the volume of the blue. So the orange balloon is filled with neon. And the blue balloon is filled with argon, and it's half the size of the neon. Okay. Which of the following best represents the mass ratio? All right, we're looking for mass of neon ratio to the mass of argon. Now we have to assume that since they're in the same environment, they have the same temperatures, right? They have the same pressures inside. Right? And different volumes, right? This volume of the neon is twice the volume of the argon. Okay, what's the mass ratio? Well, let's look at it this way. We could do some algebraic manipulations, but I think the intuitive approach is quicker and easier to understand. If this is twice the volume, it also has twice the number of moles as the argon. Okay. What's the difference in the masses? Well, the difference in the masses would be related to the difference in the individual atom masses. This is about 20, and this one's about 40. Okay. So if we have twice as many atoms in this one as we do in this one, but these weigh twice as much, they have equal masses, right? So if this is 20, say we have, let's just pick a number. Say we have 1 mole here. That means we're going to have 2 moles here. And 2 moles times 20 is 40, and 1 mole times 40 is 40. So we've got equal masses. The ratio then is 1 to 1. Okay? I think that's simpler. All right, 41. Are we regressing? What's the following? Which of the following electron configurations is different from that expected? Oh, okay. We're talking anomalies. So you're going to find anomalies with the transition metals or lanthanides and actinides. But I promised I wasn't going to throw the lanthanides and actinides at you. So we're just considering the transition metals. So what we find is when we get to, let's take the first row where we're filling the 3Ds, right? So we go scandium, titanium, vanadium, chromium. Up to the chromium, we got 3D4. But the most stable D arrangement is one of two. We have 5 subshells. So the most stable is either half or whole filled. Right? So how do we get this one for titanium to be half filled? Well, we steal it from the 4s2. Right? We take one of these and put it over here. Now we've got half filled. That's a lower energy arrangement. So titanium is one possibility. Following electron configuration is different from that expected. Well, titanium's there. 1, 2, 3, 4. Oh, I'm sorry. Not titanium. What am I thinking? Manganese. 1, 2, 3. Chromium. Okay, let's back up. Scandium, titanium, vanadium, chromium. Chromium has a 3D arrangement of, we would expect 4, but this is more stable. So we steal one from the S, put it in the D, and that's an anomaly. And that one's not there, is it? Chromium's not there. Oh yeah, chromium is there. Okay, so we found our answer. Another possibility is copper zinc. Copper would be, nominally we would put 4s2 and then 3d9. Right? Copper's 9 over it. But again, a full complement is more stable. In order to get that, we have to steal one from here. Make this 10. So copper is going to be 4s1, 3d10. But copper's not there. But if I were sneaky and put copper in there, you'd know it. 42. Okay, choose the molecule with the strongest bond. Okay. We can look at this a combination, I think, of 2 ways. One is bond strength. Okay. Maybe more than one, actually. Is difference in electronegativities. The other is bond length. How close do the atoms get to each other? So anytime you have hydrogen in there, and we have hydrogen in each one of these. So the bond length is not going to be dependent on the size of the hydrogen atom. The hydrogen atom is simply a proton, right? You can get it really close. So we've taken that one out of the mix. The size of the atom has no bearing on the bond length. But the bond length could be dependent upon it, which is dependent upon the strength of the bond, stronger bonds or shorter bonds. So CH4 is like that. And water is like this. And ammonia is like this. And HF is like this. Now, as far as electronegativities go, the most electronegative is fluorine, and then oxygen, and then nitrogen, and then carbon. So based upon electronegativity, we would expect this one to be the strongest bond. And in fact, it is. I think I better stop talking there. That's enough information. And we get down to short answers. All right. 3 samples of solid substance composed of elements A and Z were prepared. The first contained 4.31 grams A and 7.7 grams of Z. Sample 1, 2, and 3. Okay, so let's do it this way. 43. Sample number 1, number 2, and number 3. Okay, the first sample is 4.31 grams of A and 7.7 grams of Z. The second one is 35.9% A. Is this by mass? We have to assume it's by mass, otherwise we're lost. Solid substance, yeah, it has to be by mass. 35.9% A and 64.1% Z. And then 0.718 A and 2 grams of Z. Okay. The law of definite proportions. What is the law of definite proportions? It simply says that for any compound, no matter what the source, how it's made or how it's isolated, it doesn't matter. Once you've got a pure compound, the ratio of the elements in that compound by mass is constant, whatever the source. Right? My example I've used is purify water, distill water, or make water from hydrogen oxygen combustion. Either way, you get water, and the ratio of hydrogen to oxygen by mass is always the same. So if we're going to demonstrate this one, these two are already mass, right? So we could say, what's the percent of A or Z in this compound? Well, in this one, we would have to say, what's 4.31 and 7.70? That's 12.01. 12.01, 12.01 times 100 would be A to Z ratio. 4.31 and 12.01. That's 35.9%. And 7.7 divided by 12.01 is 64.1%. Right? So there we have, this one's the same percent as that one. Question is this one the same percent? So this would be divided by 2.718 grams times 100. And this would be 2.718 grams times 100. 0.718 and 2.7. Oops. Did I write that one right? Or did I read the problem wrong? Hold on a second. Right. Oh, I did write it wrong. Sorry. So the last section says that 0.718 grams of A reacted with Z, 0.718 grams of A reacted with Z to make 2 grams of the total. So Z is going to be 2 minus 7.7, 0.718. So that would be 1.28. 1.28 is actually the grams of Z. Okay. So this would be divided by 2, and this would be divided by 2. Let's see where I made my mistake. 0.718. Let's take half of it. 35.9%. And this one would be 1.28. Would be 64. Close enough. So that demonstrates that they're all the same percentage by mass. Okay. Get to balance an equation. Write the balanced combustion reaction of C2H5OH as one of the reactants. A combustion reaction always reacts with oxygen. So C2H5OH plus oxygen yields what? Anytime you take carbohydrate or an alcohol and react with oxygen, you get carbon dioxide and water. Those are facts that you need to know. Otherwise, you can't balance the equation. Okay, so if we do our budget, carbon, hydrogen, oxygen is it. We got 2 carbons, we got 5, 6 hydrogens, and we got 1, 2, 3 oxygens. 1 carbon, 2 hydrogens, and 3 oxygens. Okay. See if that's right. 9, 10, 11. 2, 7, 8, 9, 10, 11, and 6. 1, 2, 3, 4, 5, 6. Okay. So start with carbon. Now, we need 2 carbons on this side. That gives us 5 oxygens. Hydrogens. Okay. Let's see. We need 6 hydrogens on this side. It's in one location, so a 3 in front of that one will give us 6, which changes to 3, and 4 is 7. So now how do we get 7 oxygens out of that? Well, we've got 1 here already, so we really only need 6. So if we put a 3 in front of this one, that means 6 plus 1 is 7. And there's our balanced equation. Okay. The trick to this one The budget part is easy. The trick to this one is knowing what the products are. Right? Anytime you combust carbohydrate, like octane would be C8H18 plus oxygen yields carbon dioxide and water. Same thing for alcohols, C2H5OH. Those always give us carbon dioxide and water also. Big molecules like starch would be a carbohydrate. It has carbon, hydrogen, oxygen in it. Complete combustion for that one yields carbon dioxide and water. All right. Okay. Test our math skills here. Okay, we're still good. Photogray lenses incorporate small amounts of silver chloride in the glass of the lens. The following reaction occurs in the light, causing the lens to darken. So what it does is it breaks apart the silver chloride into silver and chloride ions. And like I said before, very finely divided metals, in this case, an ion of silver, are black. So that darkens the lens. The enthalpy change for this reaction is 3 times 10 to the second kilojoules per mole. Assuming all this energy is supplied by the light, what's the maximum wavelength of light that can cause this reaction? All right. So we've got this reaction. Silver chloride is broken apart into silver ion and chloride ion. And the enthalpy of this reaction equals 3.10 times 10 squared kilojoules per mole. Okay. If we want to know the wavelength of light, we've got to figure a way to reduce the amount of energy required, not to moles, but to individual molecules. Because 1 photon per break. Okay, it's got to break that one bond with 1 photon. So if we start off with that energy per mole, and this is 1 mole, so it's that much energy for the reaction, then we need to know how many joules. So if we start off with 3.10 times 10 to the second kilojoules, and this is per mole, then we got to get rid of this dimensional analysis. We got to get rid of this mole and break it down into molecule. Right, so how many molecules per mole? 6.022 times 10 to the 23rd. So now we got it down to the molecule level. That's kilojoules. The standard, the SI unit is joules, not kilojoules. So we got to break it down into joules. Kilojoules in the denominator to cancel that, joules here. That means 10 to the 3rd joules per kilojoule. So now what we have is kilojoules per molecule. Excuse me, joules per molecule. All right. So let's figure that one out first, because we got to go to a different formula after this. 3.10, 6.2, and 6.022, 6.23 divide in 1,000 times. So I get 5.148 times 10 to the minus 19 joules per molecule. Okay, that's how much energy. Remember this equation? We can find out, well, the question is wavelength, isn't it? Yeah, what wavelength? This will give us the frequency. But if we want to go straight to wavelength, we need this relationship. Right? C over lambda, which means Planck's constant times C over lambda. And if we go ahead and solve for lambda before we put any numbers in, it might be easier to do it that way. Then we bring lambda over here. Right? Bring lambda over there, put energy over there, which is Planck's constant times that over energy. Okay. So we need Planck's constant, which is 6.626 10 to the minus 34. 34. And that's joule seconds, units of measure. Okay. Speed of light in SI units, 2.9979 times 10 to the 8th meters per second. And then energy is in joules. And that's this energy right here. 5.148 times 10 to the minus 19 joules per molecule. Okay. So, denominator, numerator, denominator. This is going to be meters per molecule. So that's the wavelength in meters per molecule. So let's see, let's keep that one, and 6.626 exponent minus 34. And I want to flip that and divide. And then 2.9979 exponent 8 times. So this is 3.86 times 10 to the minus 7th meters. Okay. Did it specify? Maximum. What's the maximum wavelength of light? All right. So I converted it to nanometers, but that's a perfectly valid answer right there. Right? If we were to make nanometers, right, 10 to the 9th nanometers per meter. So we would move this decimal. Let's do it this way. 386 times 10 to the minus 9th meters. This is a nanometer. So there's your 386 nanometers. All right. Oh, you've seen this one before. In fact, you saw it today, didn't you? Okay. We won't have to spend a lot of time on this one. We'll just work through it real quick. Using that chart. So if we set up, what do we know? Well, for these three molecules, A, B, and C, A has a hybridization of sp3. That's given. Okay. B has two more effective pairs. Yeah, two more effective pairs. So if it's sp3, all of the sp3 hybrids are used up. So to get two more effective pairs, we have to go to D. So D2sp3 is your only choice for two more effective pairs. Molecule C consists of one sigma bond and two pi bonds. You can only have a pi bond if you have a sigma. If there's only one sigma, then both of the pi bonds have to go with that sigma. That means a triple bond. And a triple bond is always linear sp hybrid. Okay, so the electronic geometry is sp3 is tetrahedral, D2sp3 is octahedral, sp is linear. And the bond angles, nominally for tetrahedron is 109.5 degrees. Octahedral, it depends. If all of the positions are occupied by atoms, then you have the potential for 90 degrees and 180 degrees. So that's the best answer. And then it covers all your bases. And linear is always 180 degrees. All right. Oh, we got to balance another one. And that one looks like a bear. All right. You're going to challenge your instructor. I didn't write out any cheats on this one. Okay, 47. See if I can do this without messing up. We're starting out with potassium iodide. And let me bring it down just a little bit because I want to do something. I want to incorporate some redox tricks. KNO3. And iodine, and water. Okay. Sometimes, especially if you know that your reaction is redox, before you jump into the budget, it's useful to balance the electrons first, then work from that point with your budget method. So we know that this one is a redox because that iodine is in a compound here, and it's not over here. In fact, need the two. I got the rest of them right. Yeah, okay. So we know that iodine is going to go from -1 to 0. So it had to lose as a loss of 1 electron per iodine. Okay, before we deal with that, let's find out which one was oxidized. Loss is oxidized. We find out which is reduced. Well, let's see. 2 is taken as a -2, so that's a +2. And this is a -2, so that's a -6 total. And then potassium is always a +1, so this one has to be a +5. This nitrogen is the same as that one, nitrate, nitrate. This one's a +5. So we know that it didn't redox from here to here. It redox from here to here. Right? So it gains 3 electrons per nitrogen. Okay. And the rest of them are unchanged. All right, so now let's balance the electrons. This went from, see, 1 iodine here, but there are 2 of them over there. So at the least, we need to go 2 here, which is 2 electrons lost. But now this is 3 electrons. So in order to balance it, we need to cross multiply. If you go odd and even, then you take this 3 times that one, and this 2 times that one, 6 electrons, 6 electrons. But what does that do to this one? Well, we multiplied 2 here, so this would be 2, and this would be 2. Okay? And we don't have to worry about balancing the rest of them right now because we're going to do that afterwards. But this one multiplied 3 times. So 3 times this one, excuse me, I forgot to do that. This 2 should have been here. All right. Now 3 times that gives us 6. And 3 times this one gives us 6. Okay, so this is our new starting point. We've got the electrons balanced. Now we can go to the budget method. We didn't do this in class, did we? I don't remember doing that. So this is new. We did talk about redox, right? Didn't we do redox? Yeah, I think we did. Okay, so now we tally. We've got potassium. Now we've got nitrate here, but we got nitrous oxide here. So we've broken this one apart. That means we have to include everything as individual elements. So potassium, iodine, hydrogen, nitrogen, oxygen. All right, so our tally here is 6 potassiums, 6 iodines, 2 hydrogens, 2 nitrogens, and 6 oxygens. So that'd be 10, 22. So that's 6 and 6 is 12, 14, 16, and 6 is 22. Okay. On this side, we've got 1 potassium. We've got 6 iodine, which we should have. We did that before. Hydrogens, 2 only. Nitrogens, we've got 2, 3 nitrogens. Yep, 3 nitrogens. And oxygens, we've got 3, 4, 5, 6. Now let's see if that adds up. That's 9, 10, 18. So this is 1, 2, 5, 6, 7, 8, 9. And 9 and 6 is 15, 16, 17, 18. Did I count that right? Yeah. Okay, so I've counted everything up right. Now we balance the equation. We want to keep that iodine out till last, in case it changes. Potassium. How about we do potassium? 6 potassium here. Okay, so 6 potassium. Now that changes the nitrogens. 6, 7, 8. 8 nitrogens. Correct? Okay. Hydrogens. Looks like nitrogens, we're stuck with nitrogen. Okay, so if we say 4, if we say, let's see, 4 times that would be 8. Right? We need 8 nitrogens. Okay, it's 8 nitrogens. That's 3 times 8 is 24 oxygens. And 8 hydrogens. 8 hydrogens, 8 nitrogens. 24 oxygens. Okay, so now we've got to deal with, looks like the iodines are stable. We got to deal with oxygens and hydrogens. So how many hydrogens do we have over here? The only place we can get hydrogens is right here. Right? So if we have 4 here, that's 8 hydrogens. And then a recount of the oxygens is 4, 5, 6, and 18 is 24 for balance. Well, that was a lot of work, but it would be impossible if you didn't balance the electrons first. I've tried it. You can't do it. At least I can't do it. Maybe a computer could do it. All right. It looks like a good extra credit question there. 48. Okay, I got 20 minutes. How many more I got? Oh, good. Maybe we can get through it. One of the major commercial uses of sulfuric acid is in the production of phosphoric acid and calcium sulfate. Yep. Calcium phosphate, that's the primary mineral in phosphate rock. You can grind up just plain phosphate rock, spread it on your field, and provide phosphorus for your crops. But it's not very efficient. It takes a lot. So we hit it with sulfuric acid, and that converts all the phosphate in the rock to phosphoric acid. And then you can isolate the phosphoric acid to make a concentrated amount. Typically, though, it's polymerized into a type of a phosphate polymer, which is beyond this course. Anyway, this is the beginning step with phosphate rock and sulfuric acid. What mass of concentrated H2SO4 must be used to react completely with 100 grams of calcium phosphate? This is a stoichiometry problem. So we've got calcium phosphate. Oops, that was getting weak. Let's try this. Calcium phosphate, and this should be 2. Sulfuric acid. And calcium sulfate. Everybody knows what calcium sulfate is? Well, if you hydrate it with 7 waters, you got gypsum. And you can make wallboard out of it, among other things. Okay. Actually, in California, they take gypsum products and spread it on the ground because it leaches out the salt. They use so much irrigation water in that environment, and there's so little rainfall where they grow the crops, that evaporation of the water through the plants and other means leaves behind lots of salt. The water is not inherently salty, but if you put hundreds of acre feet on your crop, over time, what little salt is there is left behind, and that makes your soil non-productive. So they hit it with calcium sulfate, and it exchanges with the sodium on the soil particles, and then the sodium just leaches through into the subsoil and goes out of the root zone, and you're left with a viable soil. Okay, so 100 grams of calcium phosphate, 100 grams of calcium phosphate. We want to react it completely with sulfuric acid. Okay. But we want to know what mass. The question is, how many grams of H2SO4, 98% mass. Okay. That's concentrated sulfuric acid. In fact, I've got a bottle of that in our lab. And needless to say, it's dangerous. What we need to do is find out, we can't react it unless we know moles, right? So we need to know the molar mass of this. 3 times calcium, which is 4008. And then 2 phosphoruses, right? 3097. And 8 oxygens. There we go. That's going to be the molar mass of calcium phosphate. Let's see, 40.08 times 3, 3097 times 2, and then 8 times 16. 310.18. 310.18 grams per mole. So we can find out how many moles that is. Let's see. This would be 100 grams on the bottom, moles on the top. So this number would be on the bottom. We would divide that number into it. Here we go. And that's 0.3224 moles of calcium phosphate. Okay. Now we need to convert that to how many moles of sulfuric acid. All right. So our conversion factor here would be calcium phosphate and sulfuric acid, the ratio there, which is coefficients. So this is 3 and that's 1. So this would be 0.967 moles of H2SO4. So how many grams of H2SO4 would that be? We need to know the molar mass of sulfuric acid. So that's 2 times 1.01. Sulfur is 3207. One of those. And then 4 times 16. I think it's 98. Let's see. 2.02. Enter 32.07 plus and 64. Yeah, 9809 grams, excuse me, grams per mole. Now we can convert this to grams. So 1 mole is 98.09 grams times that value, which is 94.87. 94.87 grams of H2SO4. But that's pure. We've only got 98%. Okay. So if we start from this, 94.87 grams of H2SO4, and we want to convert that to, let's see, we got, this is pure grams. So in this reagent H2SO4, we have 98 grams of H2SO4 per 100 grams of sample. So it's 98 grams of H2SO4 per 100 grams of the stock H2SO4. So we just divide 98 into 94.87 times 100. And that's 96.8. 96.8 grams. Okay. And that's a lot of work. But it's a stoichiometry problem, right? We knew that with this only 100 grams, we had to find out how many moles that was before we could move over to this part. Once we got here, then we can convert back to grams, and we have to take into account this purity problem.
I'm confused.
Oh, I'm sorry.
That's okay. No, this is the answer online. At 48. But it seems like it's the same question.
Oh. Oh, that's a mistake.
That's not supposed to be
No, that's just.
Okay, that's what I thought.
Yeah, no, that's not the right answer.
Okay,
That's
just making sure.
maybe that's why I shouldn't hand it out. Yeah, no, that's That's oranges. We need apples.
You have to write.
Oh, workout problems?
So
Yeah.
that like, I'm mixing something.
That would confuse you. I need to check Brightspace. Be sure I don't have that same document in there. Okay. Let's see. That's the last one. That's the last one. Okay, this is, molecular formula. Okay. Yeah, we can do that in 10 minutes. Oops. Not with that marker though. 49. Okay. Blah, 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 blah. Ethyl butanoate. Carbon, hydrogen, oxygen. That's all there is in this compound. Combustion of 2.78 grams of ethyl butanoate leads to. So ethyl butanoate if we take 2.78 grams, 78 grams, and combust it in pure oxygen, we get 6.32 grams of CO2, 6.32 grams of CO2, 2.58 grams of water, 2.58 grams of water. And then we're also told that the molar mass is between 100 and 150. So the molar mass is between 100 and 150 grams per mole. Okay. So what we have to do in order to, we have to get the empirical formula, carbon, hydrogen, oxygen. Now we can get carbon out of this, we can get hydrogen out of this. So how do we get the oxygen? It was combusted in pure oxygen. So you can't get it from these products. It's by difference. Carbon, hydrogen, oxygen are the only compounds in this thing. So what we have to do is find out how much carbon does this represent? And the ratio that we want to cancel carbon dioxide and leave us with carbon, right? And the ratio between those two is the molar mass of carbon is 12.01, and the molar mass of CO2 is, same time, I'll just read it off, 44.01. 44.01 grams. This way, we cancel the grams of CO2 and leaves us with grams of carbon. Okay, which should be 1.72 grams of carbon. This one we do similarly, right? Water, and we want hydrogen. Water is 18.02. That cancels the water and leaves us with hydrogen, which would be 1.01. So that should be, oh, excuse me. No, there are two hydrogens, sorry. 2.02. Yeah. Here we only had one carbon, so that was valid. But here we have two hydrogens, so we need that value. And that gives us 0.29 grams of hydrogen. Now, what's left over is oxygen. And these two added together, plus oxygen will be that. So if we add these together, that'd be 2.01, right? 2.01. Minus 2.01 is 0.77 grams of oxygen. Okay, now we have our starting point. Let's see. I think I can squeeze it in here. So we have carbon, hydrogen, oxygen. The carbon amount is 1.72 grams. And this, remember before when we worked a problem like this, we had percent composition. So we had to convert it to mass. We've already got mass here. So we can work with this mass rather than converting percent to mass. And this is hydrogen is 0.29 grams, and this is 0.77. So we can convert these directly into moles. What we need here is 12.01 grams per mole, and this one is 1.01 grams per mole, and this one is 16 grams per mole. And if I do the correct calculations correctly, that's a mess. Let me do it this way. 1.72 divided by 12.01 is 0.1432 moles of carbon. And 0.29 divided by 1.01 is 0.287 moles. And 0.77 divided by 16 is 0.048 one. Oh. Is that right? 0.77 divided by 16.
Yeah.
Yep. Okay. All right. So we need to start reducing this. So we take the smallest number and divide it into each one. 0.0481, 0.0481, 0.0481. This is going to be 1. 0.04. This is 5.97 and 0.1432 divided by 0.048. And this is 2.977. Here's where we're allowed to estimate. That's 1. This is very close to 6. This is very close to 3. So our empirical ratio, our formula is C3H6O1 times N. So let's see what this empirical formula weight is. The empirical weight. So 12.01 times 3 and 6.06 for the hydrogens and 16 for the oxygen. That's 58. Okay, grams per mole. So if this is 1, that doesn't get us there. If this is 2, that gets us to 116. Equals 2. If it's 3, though, that puts us over 150. Right, so it has to be 2. And this is our formula weight, 116, and N equals 2. So it asks us for the formula C6H12O2. Okay. And that's all she wrote. So come Thursday, you don't have to show up. If you want any help, I'll Zoom in at class time and you can catch me that way. So I'm not going to set up in here if there's not going to be anybody here.
Will there be buses?
I'm sure. Let's see. Do I have a copy of these? Yeah. No, that's not it. Oh, I didn't bring a copy with me. I'm sure there are bonuses. Yeah, I'm positive there are. Yeah. Some of these that we've done today would lend themselves for bonus.
How I felt. So I was,
Yeah,